Okay, so this is for Noah. Limits, continuity, and derivatives worksheet. So basically, chapter 2 and 3. I feel like you're good with chapter 1. You guys did very well in chapter 1. You can review that stuff like yourself, but as time goes on, like our test grades have been going down because it's more and more new material. So really today we're going to focus on like the new material where it would be the most efficient. Okay, so find each limit as if it exists. So you have to look, we're approaching infinity. So can someone raise their hand and tell me like what should we use? What is the thing we use, Tal?
Exponent thing.
Leading term test. So you look at the highest exponent term on top, highest exponent term on bottom. That clock is wrong, if that's your question. It's off by 2 hours. It's 1:22.
What's the date?
It is the 10th of December. We meet tomorrow. We meet Thursday. Your test is first period next Tuesday, exactly a week from today. I uploaded probably too many things for you to like look at, but trying to make sure there's resources available for you. What? Do you want me to go make sure they are?
What is?
Mr. Henlish's class? Do you want me to make sure they're a little quieter? At least they're not in horror. Remember last year the horror where I was at my room?
Yeah.
Okay. Not for it.
Can we ask them to be quiet or no?
Yeah.
Would you like me to?
Yeah.
Making it a thing. So you like C to rewrite it. So you use chain, not product rule. Because if it's just one person, I would go up to you and talk to you individually, but it's not. Okay. Hurts. Limit as x goes to infinity. So we use, as Tal said, leading term test. Which is bigger, x squared or x cubed? All right. What was it? Bilbo Baggins Rover, bigger on bottom.
Bobo button.
Yeah, no, that's for roots. That's for roots. So here, bigger on bottom means goes to 0. So the limit is going to 0. Bigger on bottom, bigger goes to 0. All right, bigger on bottom goes to 0. Bigger on top, there's no limit, goes to infinity, doesn't exist. If they're the same exponent, it'll just be the ratio. So imagine the top was 3x a third. If that was a third instead, it would be 3. If the top was bigger, limit would not exist. Okay.
Or would we do infinity?
We would say infinity comma does not exist. All right. The answer is 0. We're just going through the other like options. What if I change the problem so blah blah blah. Okay. Next, limit as x approaches infinity of sine of 2x over 3. So let's think. How could I? We know the limit as x goes to 0 of sine of 2x over 2x would be 1, but we don't have the same number.
Interesting.
So what I would like to do is write the bottom as like 2. So if I multiply by 2 over 2, am I changing the problem? It's just multiplying by 1. Just multiply by 1. So I could say this is the same thing as the limit as x goes to 0 of 2 times sine of 2x over 2x, and then what happened to my 3? Just pull it out, because this portion right here, the limit would be 1, and then you just multiply the constant of 2/3.
No.
Because if I multiply the bottom by 2, I could say, oh, okay, well, x times 2, and then have the 3 out front. So this is one of the properties of limits. I can split it. I mean, this is not necessary, but I could say, oh, since there's a constant 2/3 in front, I can move it out front, and then I'm just taking the limit as x goes to 0 of sine of 2x over 2x. And we know sine of number times x over same number times x, that's 1. So since this limit is 1, it's just going to be 2/3.
Is the entire final, like, are we going to do 2 parts, like calculator and no calculator part, or is the entire final?
Ask me tomorrow.
Okay.
I made my finals for my other 2 classes, but I need to finish grading your test first. Yeah. You know for sure you'll have at least a, you know for sure there'll at least be a portion where you do have a calculator. So let me think about it first. Yeah.
I remember like from this chapter, if it was like sine of 2x over x, then it was
Multiply by 2 over 2.
Oh, okay, I see.
Because the 2 on the bottom goes for like sine of 2x over 2x, and then you have a 2 in front. Okay. Yeah. All right, so this one, we try to plug in the values like straight into it. So normally, we would try plugging this in and I would get sine of 0 over 0. So technically that's indeterminate form. I mean, we normally try to plug straight in, but secretly we know there's a whole trick with, the sine of x over x. So if I tried to plug in straight up into the limit now, I'll have 0 over 0. That's indeterminate. So I have to do something special. Whenever you get indeterminate form, so plug in gets indeterminate, there's a couple options you have to do. You either try to factor out something or multiply by the conjugate. Even though the radical's on bottom, we can multiply by the conjugate. So I'm going to multiply by root x plus 3 over root x plus 3. Now note, I'm not going to fully factor the top. I'm going to leave it. I'm going to leave it as x minus 9 times root x plus 3. And the reason I do that is because it should cancel out. That's the whole reason we multiply the conjugate, so we have a factor that will cancel. So, trick. Let's make sure we know how to FOIL. Root x minus 3 and root x plus 3. Since it's a difference of squares, the middle two terms of your FOIL will cancel out, and I'll be left with x minus 9. Because root x minus 3, root x plus 3. So make sure you understand that. This is just going to be root x squared plus 3 root x minus 3 root x minus 9. The middle two cancel. Square root and square cancel, so x minus 9. Those guys cancel out right here. And I'll be left with the limit of root x plus 3 as x goes to 9. And then when you plug in, then you get root 9 plus 3, which is 3 plus 3, so just 6. Do we remember these rules? Maybe. Alright, so a little selfish hint, the easier it is for me to follow, easier points I can give you. If I can't follow your train of thought, I don't know if I can give you your partial credit. So, try to make it logical. If you need extra paper, literally ask for as much extra paper as you want and make it so it's really easy to follow the logic. Cool. Let's try the next one. So notice we're going towards negative infinity. Whenever we're approaching end behavior and limits, it's when we're approaching infinity and negative infinity. So to see what the limit would be, see what the end behavior, I think Tal said it before, we use the leading term test, but you have to make sure you picked the term with the highest exponent. This time we have x cubed over x squared. So bigger on top means, right, it means it doesn't exist. Is it going to be approaching infinity or negative infinity? Negative infinity. Sorry, negative infinity, because x cubed over x squared, literally you're just left with 1x. So we're going to be approaching negative infinity, and then we have to say it does not exist.
So if it was x to the fourth over x squared, then it would be infinity?
Yep, because the negative would times negative is positive.
So whenever you see a negative...
Because if you think about it, hold on, if you think about it, what is x cubed look like?
Yes.
Look at the end behavior. X to the fourth. Oh, they both face the same way. That's why.
So if it was x to the fourth on the top?
Yep.
Oh, so if it's even?
Yep.
Oh, okay.
Because then you're multiplying negative by an even number of times. Meaning, if you have a negative times negative, turns positive. If you have a negative times negative times negative, it stays negative. Huh?
Yeah.
We did. Yeah, last year. For sure. Okay, so are we ready for the next one? Okay. Limit as x goes to e, so whenever we're approaching a number, we try plugging it in. Do we know what ln of e is equal to? 1. That should be a nice, easy question.
Wait, really?
Yeah.
Oh.
Because remember, ln is natural log. It's literally log base e of e is equal to the exponent. So e to what power is e? 1. All right, natural log.
It's okay.
Okay, so this is like general, like little spattering of limits. So you can always like go back, work on the limit stuff. Hopefully this will jumpstart your review. Next, determine intervals where the function's continuous, x values where the function's discontinuous, and identify each type of discontinuity, removable, jump, and infinite. So the way you, so first off, to even have a jump discontinuity, you have to have a piecewise function. Jumps only occur with piecewise functions. Now, I'm not saying every piecewise has a jump discontinuity, but to even have a jump in the first place, jump discontinuity has to be a piecewise. So, number 6, we already know it's not going to be a jump. So, difference between a removable and an infinite discontinuity. If your factor cancels out on top and bottom, whatever that x value or whatever that factor's like solution is, that's where you have a removable. If you have a factor on bottom that doesn't cancel, that's where you have an infinite. So let's fully factor this and let's see what we have. If I fully factor the top, what adds to 1 multiplies -2 would be x plus 2 and x minus 1. So notice the x minus 1 cancels out.
That's a removable.
So this is a removable. This means we'll have literally just a circle hole, not any asymptotes, just a hole at x equals 1, right? Because you set x minus 1 equal to 0. So it says, okay, add 1 to both sides. We see when x equals 1, we have a removable discontinuity. So A, find the intervals where it's continuous. Well, we found the one place it's not continuous, so it's going to be all numbers except that one. So I'm just cutting out the one place where it can't be part of my domain. And then B is saying, hey, tell me what x value it is and tell me what type.
Oh my god, I stole it.
Okay. Do we have questions on this so far?
Yeah.
Okay. Nice, crisp review view. So if you're like good with this, then you know you don't need to like spend too much time reviewing it. But if you're like, what the heck? You know you have to look over it again. I'm trying to help you know where to review. Number 7. So if I look at my two functions, x squared plus 3, that's a polynomial. That's just going to be continuous. 2 plus x is a continuous line, right? It's a continuous function. The only place I could possibly have a discontinuity is at the point where I'm switching between the functions. So at my, what do you call it? The border point. What do you guys call it? Where they meet, like literally at the place where I'm switching from one function to another. So, what? B. B is in boy. What? She asked what period, so we said B. So how can I see if I'm going to have discontinuity at the place where I'm switching? Plug in. See what the y value would be. If I'm approaching the same y value, it's continuous. If I'm approaching different y values, it will be a jump. So if I plug in 1 here, 1 squared plus 3 is 4. Plug in 1 here, 2 plus 1 is 3. They do not match. So I'll have a jump discontinuity. Roughly what this will look like, something like this. And then plus 1. And then like that. That's what this graph looks like, roughly. Not exact numbers, but you see. We literally have a jump. I had to pick up my pen to actually draw the graph. That's what this means. One of my places ends at 4, the other ends at 3. So this one I did because I do have a, wait, what?
Like, when it asks for the x value and the function,
well, if it was continuous, then you would say no discontinuities. But B is asking for x values, what? Yeah, x equals 1.
So it's whatever is your function?
It's wherever we have a discontinuity. So I have a discontinuity at these points. Although the function has a y value.
How do you know that one? Like, are those numbers always going to be the same, I guess?
So whenever you have a piecewise, you have to look at your switch points to see if they're continuous or if there's actually a jump.
Right, but is it always going to be the same number?
I could put like x is less than 2, x is greater than or equal to 2. Oh, like, are these numbers gonna be the same?
Yes.
I mean, I could make this like 2, and then it would be even more of a gap.
Then how do we know that?
Then it for sure would be a jump discontinuity between 1 and 2. Because there's literally, it would be like this.
No, yeah, no, I understand that it's jump, but I don't understand how we know.
There'd be a gap right here.
Like when you said x equals 1.
Oh, well, in order for it to say the x value, I had to have only one value be discontinuous. If I would say the interval of discontinuity, I would say, oh, from 1 to 2. I guess I don't know what you're asking.
Yeah. Like
I don't understand what you're asking me.
It's discontinuous on the x.
So, discontinuities,
Like if you have
look at the bottom versus a root, a radical. Radical is like a square root. I don't know what you're asking me.
Like, I understand this, like why it'd be at x equals 1. For here, let's say you had 1 and 2. How would you know where on the x-axis it's discontinuous?
It would be between 1 and 2 because it's not defined.
How do you say that? Between? Yeah, that's what I'm asking. So, like,
Well, I didn't. But I asked for a specific x value, not an interval. That's why I didn't give you between 1 and 2.
So you wouldn't. So it would always be the same. So you're always going to give us the same number here.
No. But I would word the instructions different. I would word the instructions different.
And then what would be the instruction?
What? Tell me the places, all of the intervals, all the x values. Tell me all of the x values where it's discontinuous.
1, 2. How would we write between 1 and 2?
What are you asking me? What?
If they're different numbers, it can't be continuous. Because if it only goes to 2 on 1.
So you're asking how the directions would be totally different.
How would I write like it's between 1 and 2?
So you would say from like 1 to 2. 1 to 2, undefined.
Yes.
But like I can't make this a 2 with the directions as written.
Yes.
Because it doesn't make sense with the directions as
Now I
written.
understand everything. Can I just have one clarifying question?
What?
So no.
What?
I don't ask 5 questions. No.
What?
See the 4 and 3.
Yes.
If they were the same.
It would be continuous. It would have no discontinuities.
Okay, then just
Because that would mean I have this, and then I have a point right here.
From the same spot, right?
Yeah, and that'd be continuous. Okay. Yeah. All right. So there's only one place where it's not continuous, and that's 1. So we just cut that out. That's it.
Wouldn't it be bracketed though because it's on the second one because it says
No.
x is greater than or equal to 1?
No. So although it's defined there, we don't know where it's continuous. So technically, it can't equal 1. Although it has a y value, it's not continuous at that point. Subtle. It's subtle. Although, if I was asking for a domain, the domain would be all real numbers, but the intervals of continuity is not. That's a very good question. If you're talking, you should probably listen, because I'll repeat it 1 time, and that's it. So, if I was asking for a domain of this function, it'd be all real numbers, because I have a y value for x equals 1, but I want continuity. Where is it continuous? It's not continuous at x equals 1, because that's where a jump occurs. Although we have a y value, it's not continuous there, and that's why I cut it out. Yeah? Okay.
Why?
Subtle, very subtle.
So it could be all real numbers.
For domain. But if I'm asking for intervals of continuity, for intervals where it's continuous, I'd have to cut out x equals 1. Because it's only continuous from negative infinity to 1, and then from 1 to infinity. Because at x equals 1, we are switching functions.
And if it jumped and it was a whole, like it wasn't x is greater than or equal to 1,
If it's just greater than 1,
then the domain wouldn't be all real.
and the domain would match the continuity.
Okay.
Yeah. Okay. So, what do you... Okay. Determine intervals where the function is differentiable, aka you can take a derivative. So we got to think back. This is a little different than being continuous. So to be differentiable, to be able to take a derivative, it has to be continuous, but it also, you can't be approaching a derivative that's vertical, aka, remember like the cube root function? We are approaching a vertical tangent. This is a vertical tangent. Because if you think about it, hold your hand out and then see the slope. Make tangents with your arm. Oh, as we get to this middle point right here, right? So Slope, 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 slope. Oh my gosh, we're approaching a vertical tangent. We don't want a vertical slope. Another thing is discontinuity. Okay, if you literally, this deals with, okay, it has to be continuous to take a derivative. So if you have a discontinuity, I mean, it's not going to be continuous. You have to be continuous to even think about taking a derivative.
So for A, it would be discontinuous, right?
I'm going to wait a sec. Wait a sec. Okay, a cusp and a corner. So a cusp is the bird. You're approaching a slope of negative infinity and a slope of positive infinity at the same point. And that's the difference between a corner. A corner is just you're literally having two, it could be an absolute value. You're just having two different slopes. So I could have a slope of 0, then all of a sudden a slope of 2, and this is a corner. A corner is you have a slope, but they're not the same as you approach a certain point. So let me show you that. So a cusp. You know what I'm doing with my arm? I'm making a tangent line, right? I'm saying, here's a slope at this point. Here's a slope at this point. Okay, make sure we're all clear. So slope, slope, slope. Oh, I'm approaching a negative infinity as I come from the left side. And as I come from the right side, I'm approaching positive infinity slope. So cusp where you're approaching positive, negative infinities versus a corner, you have a nice 0 slope, and then instantaneously you go to like a 2 slope. Your slopes are defined, right? You're not going to infinity, but you're approaching 2 different slopes. So that's weird. That one's where you keep getting tripped up.
Different. At the corner, you can't find a derivative.
Right, you don't have one derivative because you're switching from one slope to another slope.
Okay.
So that's a corner. Cusp. So corners, you actually have slopes, values, where cusp, you're approaching negative and positive infinity. Vertical tangent, you're approaching a vertical tangent in the middle. And discontinuity. Clearly, if you have a infinite discontinuity or a jump or a hole, at that point it wouldn't be differentiable. So this is all the 3 discontinuities we just talked about. And then to actually take a derivative, has to be continuous, and it can't be a vertical tangent, cusp, or corner. So it's like even more rules. So we want to find where it's differentiable. So let's see if this is even continuous. If it's not continuous, we can throw it out right away. So if I'm looking at x squared by itself, polynomial, all real number domain, continuous, 6x minus 9 by itself, polynomial by itself, all real numbers, perfect, continuous. But the fact that this is a piecewise function means there technically could be a point. Either I have x squared, and where it leaves off, another one begins. Or I'm going to have a parabola, and then I'm going to have a jump. So it's either going to be continuous, like on the left it's showing, or discontinuous. So let's even check. For it to even be differentiable, it has to be continuous. Okay, so to check if it's continuous, I have to check, is my y value where I'm exiting the same as the y value where I'm entering? Yes, jump discontinuity right here. We did a jump.
Wait, a jump differentiable. A jump differentiable.
So if you have a jump discontinuity, it is a discontinuity.
And the discontinuity is
will not allow it to be differentiable. Will not allow it to be differentiable. Meaning you won't be able to take a derivative. Okay. So let's see what this value would be. 3 squared is 9. 6 times 3 minus 9 is 18 minus 9, which is 9. Okay, we're approaching the same number. Meaning, where one of these is leaving off, the other guy is coming in and taking over and picking up. So it's continuous. It's actually continuous. Wonderful. So, okay, so we know it's not discontinuous if it's continuous. Does this have a cusp? Hi. Oh, okay. Are you crying to her? Oh my gosh. Don't cry to her, you guys. You're doing fine. Don't cry.
Who's crying? Who's the weakling? Me. I cried twice.
You didn't even give me a chance to answer. You didn't give me a chance to answer. You just asked me 5 questions. Bombardment. Oh, hello. Okay, focus. Here we go. So, does this have a... Are you going to tell everyone your business? You don't have to.
Spill the tea, spill the
Show and
tea.
tell.
Regarding Shanique, because it had to do with my actions that she was slightly involved by. Okay, no, now I have to.
So let's go through this. Do we have a discontinuity here? No, it's continuous. We just proved it. Do we have a cusp? No flying birds. We're good. Do we have a corner?
Do we have a calculator?
No.
I'm gonna answer this tomorrow. Do we have a corner?
No.
No.
No. So you know what it is?
Do we have let's see, vertical tangent?
Well, I'd say you have to since it's the last option.
No?
Is there another one?
So none, exactly.
Oh.
B says the x values where the function's not differentiable, none. It's differentiable everywhere, meaning the interval where it's differentiable is negative infinity to infinity.
Oh, cause it's none.
Because it's Kirby.
Oh,
Yeah.
I see. My bad.
No, I just.
So
Why
to
would it be a
prove
corner?
it's a corner. Good question. Good question. I was waiting because you guys were too. You're like, nah, it's not a corner. No. What is the derivative at? What's the derivative of x squared?
2x.
And what's the derivative of 6x?
It's gonna be
6. So I know.
Oh my god.
Oh my god! Stop talking. Stop talking, please. So, in order to be a corner, you have to have the same slope from both sides. Otherwise, it'll look like this when I look at the derivative. So, tricky trick. I was going to see if anyone popped up and said, wait, corner means two different slopes. We might have two different slopes because we have two different equations. But no. It means it has two numbers that are slopes, but the numbers aren't the same. Versus, like, this is a slope of maybe like 0, slope of 2, versus the slope here is negative infinity, and the slope here is like positive infinity. Versus here, the slope is like infinity. So the difference between cusp and corner is corner has two defined slopes, they're just not the same thing. So in order to not to be a corner, we have to make sure the slope on the left side is equal to slope on the right. So I'm proving the slopes are equal. Slope on the left is equal to slope on the right. At what x value are we switching from one function to another? 3. If I plug in 3 for x, I have 6 equals 6. Proving it's a nice smooth transition. The derivatives will be a nice smooth transition.
So if it's smooth, then it's nullable.
Right. If this was x cubed, and let's say randomly they were okay. If I had the same y values, but different slopes, then it would be a corner. Okay. So that was a tricky trick. Corners, if you look on the left of a corner, you'll have a defined slope, a number. If you look on the right of a corner, you'll have a number. The issue that they're not differential is because at that one point, you're switching from one slope to another. They're not the actual same slope. That's a corner. Versus a cusp, you're switching from a negative infinity slope to a positive infinity slope. Solid. That was good. That was definitely know what you're doing. I'll give you a participation point.
Me?
No, she was the one that said corner. She's the one. She's the one that was like, wait, it's a corner. No. This is.
You said first.
I said I'll give you. Yeah. And say you all. Alright, let's look at h of x. Let's see. So, this is to the 5th power. This is an odd root, which means even roots are like square root. Odd roots go like this. Vertical tangent. Well, wait. To the 5th. You know what I forgot about? 4th in the middle. Big dog in the house or whatever. Top dog in the house. So, 4/5.
Yep.
So wait, if I don't just have a nice like 5th root or 3rd root, if I have this other like
A
fraction, this is actually going to look like what?
A corner.
It's going to look like a cusp.
Oh, a fraction is a cusp? Okay.
Do you want me to pull up the notes? I'll look at
It's something you just gotta remember is that if it's a fraction.
What is this? Chapter 2? Chapter 2.
Okay.
I'm just going to show you.
If it's a
I don't remember where this was from. I just want to show you the rules. Let's try 2.
Yeah.
Just remember root. It's root.
Yeah. Alright, back.
Nah, I guess this is not it. 2. Maybe it's section 3.
Like, you know the old TVs or whatever, like static.
You can also say it looks like
Like
seats on a bus.
Yeah.
No, it hit me right. I want to get a sweatshirt that has like a blue pattern, you know, the classic.
All the rules in your chapter 2 notes, like you guys have your notes. I think this is chapter 2, pretty sure. Maybe 3 or 4. Discontinuity, differentiable.
I have one. Never wear it. I bought it all.
Oh, is this chapter 3? No, it's chapter 1. I'm trying to think where this is. Maybe it's chapter 1. Because there's the rules. I literally just want to show you the rules. There's a whole page of just rules. Maybe it's beginning of chapter 3? I don't know. Maybe, you know what? It was beginning of chapter 3.
I remember chapter 1 was recapping the limits and whatever. Chapter 2 was using the limits for stuff and things. And chapter 3 was
It was so long ago. That's why I thought it was chapter 2. Derivatives, differentiability. Okay, so here we go. Here are the rules. So, cusp. Cusp versus cornet. That'll give you more information. So if you have the fraction, it's gonna be more like a cusp. Versus just alone, it will be the vertical tangent. You're like not even facing the board. Gabe, sit up. Come on, put your hood down.
My hood is down.
Was I looking at you when I said that? No, context clues. I was looking at Elliot. Okay, I make eye contact when I redirect. Okay, so here are the 3 things. This is page 6 on the chapter 3 part 1 notes. Like literally all the notes are uploaded, all the solutions to the notes are uploaded. You could look at it. Okay, so cusp. Where is this cusp occurring? At 2. How do you know? Yes, because you look at the inside and you set equals 0. X minus 2 equals 0. Add 2 on both sides. You see at x equals 2, that's where the cusp is occurring. The cusp is occurring at literally like the origin or vertex. The only issue is we're shifting everything to the right by 2. It's a transformation. So instead of having the 5th root of x to the 4th, because then the cusp would be at x equals 0, we're shifting everything to the right by 2. That's what x minus 2 in parentheses. Shifting is opposite what you think. Transformations. It's in chapter 2, or I'm sorry, algebra 2, algebra 1, and pre-cal. Find dy dx. Simplify each answer. Oh, we didn't finish. Yeah, intervals of differentiability, you just cut out 2.
So negative infinity to 2.
Huh?
It's like discontinuity.
So, because this is differentiability. Because something can be continuous and you won't be able to take the derivative. Like for instance, if I have a graph that looks like this is continuous, but it's not differentiable because at this point right here, I'm changing my slope. This is a corner. If I have a graph like this, although this is continuous, it's not differentiable right here where I have a vertical tangent. Yeah, that's why it's a little different. It has to be continuous on top of other special cases. All right, dy dx. Simplify each answer. So going through like more chapter 3. This is a product. This is a product. Because I have x squared times sine x. What if I instead, don't write this, what if I had sine of x squared? Is this a product?
No.
No, because this is sine of x squared. Exactly. Chain rule. No, you're right.
That's my playlist thing. Why are you saying that?
Okay. You have to make sure you recognize.
Yeah, something though. That's my
It's like focus. It's more than 5 seconds, and all I'm asking is some focus. Okay. So this is going to be a product rule because I have 2 different functions being multiplied. Something people struggle with, and you need to write this down and like go home when you're alone, not around anyone else, and be like, is it me? Am I the problem? Am I the one who keeps doing this? Like, do I understand how trig functions work? Where trig functions, you always have to have something in here. You can't just have sine by itself. It has to be sine of something.
It's like hugging it.
Yes, yes. Sine, tangent, cosine, they have to be hugging something. Exactly. What?
I'm so good at all these analogies.
So it has to be sine of something. I'm going to get to you in a moment. So if I have sine of x squared, this is not product rule because it has to be sine of something inside. You can't just get the trig function by itself.
Makes sense when you're saying that.
Okay. So this is what I said. You got to go home by yourself and think about, like, do you understand what it means to take sine of something, right? You can't just have sin by itself. It's missing its other half. It's got to always be hugging or attached to something. Okay, yes.
Can I help you with the poem for participation?
No.
Why?
If you have a good insight that I'm hoping, like I'm planning on people to like recognize, like the fact that I was rushing through and trying to see, do you actually understand what a corner means? JK, you just say, yeah, not a corner. Like, no, you have to check. Does it have the same derivative? Like, you have to make sure you do that. For number 8? Yeah, so if you recognize something like that, sure. Okay, y equals x squared times sine x. I'd like to get through this a little more.
U and V, and then
Yes.
The derivative.
So I have u and v. So u is going to be x squared. The derivative of u is going to be 2x. V is going to be sine x, and then v prime is the derivative of sine x, which is just cosine x.
I have a question.
Yes?
Why doesn't the X go away? 'Cause isn't that
Derivative, power rule. 2 goes down times x. X squared, bring the 2 in front. So 2 times, and then you subtract 1. This is just 2x the first, which is 2x.
No, I'm talking about for the cosine.
Because it's sine of x. Derivative of sine of x is cosine of x.
One is having X, and then
And cosine of x is negative sine.
No, because cosine and
Yeah.
sine and tangent have an extra strong hug.
because they're really needy.
Because it's English now.
Okay.
What would you do if
What?
Well, I already did that, and I just wanted to
Guys, Tala's asking a question. I can't even hear her. You asking a question? Oh, what are you saying? You're just talking to yourself? Okay. Okay, so product rule. U v prime plus v u prime. So I have x squared times cosine x plus sine x times 2x. So I would just rewrite this and say x squared cosine x plus 2x sine x, and that is the answer. That is what y prime is equal to. So derivative of sine of x is cosine of x. So technically we could try to do product chain rule. Derivative of sine, cosine of x, you leave the thing inside. Derivative of x, 1. So technically we are doing chain rule, we're just multiplying by 1. You just didn't know it yet. Okay, so that's that one. Next one should be a little bit easier. Y equals 3 to the 3x, e to the 3x. So y prime. So you do itself times the derivative of 3x. Derivative of 3x? 3. So it's just 3e to the 3x. Awesome. Now, we want y prime. Let's go ahead and let's do all of the power rules. Bring the 3 down. Subtract 1. Bring the 2 down, multiply it. Subtract 1. Derivative of negative 9? 0. So that's it. This is the answer.
You don't have to bring the 3 in front? Or,
I did.
The 2 in front of the 3?
I did. Wait, what?
No, because that would be the
Because
second.
it's 3 oh.
That'd be the
So
second
move the
derivative.
3 down. 3 times x squared. Negative 2 times 2 is negative 4 times x.
Okay.
Cool. Alright, let's try the next one. So, y prime. So this is, if I just had ln of x, the derivative would be 1 over x. So I have ln of root x plus 1. So the first thing I'm going to do, so maybe it would be easier if I wrote it a little different.
You start with 1 over root x plus 1.
Well, let me write it a little different. So let me say ln of x plus 1 to the 1/2 power. Using rules of logs, power rule for logarithms, this is the same thing as 1/2 as ln, 1/2 of ln of x plus 1. So that helps. That helps a little bit, because then when I do y prime, it's going to be 1/2 times 1 over x plus 1. Yes?
Is this not changing where you multiply?
So we could get the same
is
answer if we did
changing.
that.
Like if no, but see how you have ln parentheses x plus 1? Oh, it's just 1.
Yeah.
Technically, is this a change? Like, if that was a
Technically, yeah.
But okay.
If this is like ln of 2x plus 1, we'd have to be multiplied by 2 at the end.
When you take ln of both sides.
When?
you have okay. No, it's not you.
When you have
Right.
like y equals x to some power of x.
Yeah.
Yeah. Cool. Okay. So, cool. I can just rewrite this as 1 over 2x plus 2. Because you just distribute the 2 times x plus 1.
Why do you keep the, when you're finding the derivative, why do you keep the 1/2?
It's being multiplied. If it was adding 1/2, I'd get rid of it, but it's being multiplied. 1/2 times ln of x plus 1. It's the same reason up here we did negative 2x squared. We took negative 2 multiplied by 2 times x. If it's being multiplied, we just keep multiplying it. Cool. Okay. Now, how many problems do we have left? All right, number 14.
I still don't understand why you think
Uh,
Oh, what?
So no, quotient rules for 14. That's what they're saying. 13. You don't know what 1/2 is being multiplied. Think about if this was 1/2. Think about if this was 1/2 x to the third.
Oh, they're pink.
Okay, if this was 1/2 x to the third, you'd bring the 3 down. You would take 1/2 times 3 times x squared. If it was 1/2 times this, so you're multiplying the derivative by the number, the constant out front. Since this is a constant out front, we're going to multiply by it.
Oh.
Okay. Okay. So I think Tal said quotient rule, cool, because we have one thing divided by another. So, yeah, you could do quotient rule. You get the same answer. This is pretty short, where I'm just going to rewrite it as 3x over x squared plus 2 over x squared. And then this is the same thing as saying 3 times x to the negative 1 plus 2 times x to the negative 2. That way I can just use power rule. But you know what? This would be a good opportunity to use quotient rule, so we'll get the same thing. What? Well, negative 3 times x to the 0, or no, minus 1, x to the negative 2, minus 4 times x to the negative 3. So that means, y prime is going to be negative 3 over x squared minus 4 over x to the third.
Could you not leave it like this?
No, because it's not fully simplified. Like if it's just x's to some negative exponent, you can move it on bottom. Versus if you had, I mean, to be technically be simplified, you shouldn't have any negative exponents. Yeah. Okay, if we do quotient rule, we should get the same thing. Let's do quotient rule.
Wait, I have a question before we move on to it.
Well, do you want to do quotient rule? I have a whole worksheet for that.
Okay, so then.
What? What's wrong?
Could you do 3x plus 2 times x to the negative 2?
Yeah.
That works too. Okay.
Yeah, you got the same thing because then you made it a product.
Yeah.
Yeah.
Plus 2. But that's the right way to do the product, like when you're multiplying the exponents. I know.
Yeah. When you could, instead of having divided by x squared, you could multiply by x to negative 2. Yeah. Because you'll get the same answer. Yeah. Okay. So, do we want to do a quotient rule, or do you want to just wait for the worksheet where it's like quotient rule? Okay. So y prime for what? Did you use quotient rule?
Yeah.
It's the same thing. It's just if I make it a common denominator.
Negative
3x.
4 over x cubed.
Did I mess up the negative? No. So plus 2 over x is negative 2, negative 4. So if you had negative 3x minus 4 all over x cubed, it would be good.
Yeah, plus 4 over x cubed.
Did you do take the quotient rule?
Wait, I didn't distribute.
Huh? You didn't distribute?
No.
Yeah, you didn't distribute.
I did distribute.
What?
3x
Negative 3x minus 4 all over x cubed. So make it have a common denominator here. It'd be the same thing. Because this would be negative 3x over x cubed minus 4 over x cubed. So this is just negative 3x minus 4 all over x cubed. Okay, well, I mean, if you want to do quotient rule, you can do it. Do you want to go on? Let's go on. Yeah, I have another worksheet I didn't pass out. Implicit differentiation. Implicit differentiation. So, whenever we have an x, what do you need? Just talk to him. What do you need? Okay. Do you need something?
No.
No, okay, then let's focus. So, use implicit differentiation, find... Ooh, okay, you're done now, so let's keep going. Use implicit differentiation to find dy dx. So, if you run into an x, differentiate like normal. Take the derivative. Elliot, sit up. If we run into a y, sit up. Sit up all the way. Okay. If we run into a y, you tack on a y prime. So, let's differentiate this whole thing.
Even if the y is by itself.
Yes.
Especially
You take the derivative of it and then tack on
let's say you have the equals y, it would be equals y.
prime, which is what we normally do. Yeah. But this is if y is, it's not just equal to y. If it's like, oh, y squared and like, yeah. All right, so derivative of 2x is 2 plus, oh my gosh, I got a product rule here. So multiply by x times derivative of y, which is y prime, plus y times derivative of x, which is 1, equals derivative of y squared is 2y times y prime.
Whoa, wait a minute.
Well,
No, never.
this portion is product rule of this.
Okay, I
Yep.
You tack on a y prime.
Okay, next thing. Get everything with a y prime on one side, everything without a y prime on the other. So, I'm going to subtract xy prime on both sides. That way, I have 2 plus y equals 2y y prime minus xy prime. Now, you're not going to believe the next part, but on the right side, there's a common term, a common factor. Factor out y prime.
Oh, and then divide.
Yep. You okay? Oh, okay. Sketchy. 2y minus x. I'm just worried because you're walking so slow. Where do you hurt? Oh. Cool. So we see y prime, which is the same thing as saying dy dx. Notice the problem asked you to find dy dx. It's going to be 2 plus y over 2y minus x. Cool. How do you feel about that one? Okay. We're going too fast, too slow. What do you think?
This is the hardest derivative part.
The implicit? Yeah.
No, she said that she can do this one, but not the derivatives.
It says use derivatives. Questions on this one? So I know I've been hitting these pretty hard. Logarithmic differentiation. So this should look familiar. This is exactly one of the ones in your notes. So, logarithmic differentiation. First, we must take ln of both sides. Yes, that's the next step. What should we do? Yes, use power, rule of logarithms, to move sine x in front. Ln of y equals sine x times ln x. Then, got to use the old power rule because we want to take the derivative. So derivative of the left side, 1 over y times y prime. Derivative of the left side, well, we got to use product rule. So cosine x ln x plus sine x times 1 over x. So to get y prime by itself, multiply both sides by y. No, because that's the limit as x goes to 0 is 1. So the value of the function as we approach 0, sine x over x is 1. So, but now you see why that's a specific thing we talk about, because this comes into play. Cool. So in like later courses, or maybe later in the year, we can get to that. And then, oh, we actually know what y is equal to from up above. It's equal to x sine x. Wonderful. And this is the last problem, right? 17?
Yeah.
I think so. Perfect. Okay. I feel like this is what we struggle with the most is derivatives. The rest of the stuff is like, you've learned it at least in 1 to 2, maybe 3 other classes. Like, equations of lines. You're probably bored of it by now. Some of the trig stuff, right? You started learning in geometry. You hit it hard in algebra 2. We hit it hard in pre-cal. So I'm confident in your ability in chapter 1. Trying to help you be confident in your ability in chapter 2 and 3. Questions over 16 before we do 17? Okay, you'll recognize 17 is very similar to a previous problem you've done. Find where x values only, the graph of f of x has horizontal tangents, meaning the slope is equal to 0. Well, to find the slope, we take the derivative. So f prime of x is going to be 1/3 times 3x squared plus 1/2 times 2x minus 12. Alright, so I'm just going to rewrite this as x squared plus x minus 12 equals f prime of x. Okay, step 1, coolio. I'm going to move this up a little bit. Found the derivative. Now, I want to know where are the x values where the slope is 0, aka where the derivative is 0. So if I set this equal to 0, I can solve for the x values where they will be 0. So loud. What? It's fine.
How does he have the energy? I have no idea. He's a 3.
Be nice. That's not nice.
Being young. I wish I was young. Isn't he a full-grown man? He's 40, Anthony. I just don't know that. He's 40? I think.
Okay, cool. So these are the two values. I found the two solutions where this is actually equal to 0. So that is like a general review of limits, continuity, differentiability, all the rules of differentiation. Of course. Tomorrow you'll get your test back. Hopefully we'll spend maybe 20 minutes going over specific rules of power, product, and quotient rule. Maybe throw in some chain and other questions from the general review. Okay. You guys can go 2 minutes early, go to the bathroom or something.